we are the group 7 and we are assigned to discuss about the chapter 8 entitled Principal Geological Factors Affecting Certain Engineering Projects. By the way, I am Kimberly Ann Vivigonte and I will be your first presenter. I will discuss from the first topic, which is stability of slopes and cutting, to the types of failure of natural rock slopes. The first topic is about the stability of slopes and cuttings. So what is slope stability? Slope stability is the potential of a naturally occurring or engineered soil slope to withstand ground movements. We have an example of engineered soil slope. We have an embankments, cuttings, open pit mining, excavation, and landfills. We have also the stability of cutting in rock. So the stability of cutting in rock is usually dependent on the occurrence of joints and other planes of weakness, and on the amount of cohesions and frictions across these planes. We have geological factors affecting the stability of a new excavation. The static conditions that control the initial and also the later stability of step face cut into soil or rock, in which may determine the need for support or remedial treatment are as follows. First we have the shear strength. Shear strength by definition is the ability to resist forces that cause the material's internal structure to slide against itself. So shear strength of the material forming the cutting is the stability of cutting in a rock that is usually dependent on the occurrence of joints and other planes of weakness, and on the amount of cohesions and the frictions across these planes. We have also the structure of rock and soils, and specifically how any planes of weakness are orientated relative to newly exposed face. For example, we have horizontal bedding planes in poorly jointed sandstone often give near vertical faces which are stable, whereas faults or joints striking parallel to the new face and dipping steeply towards it. It will probably be planes of movement or potential instability. We have also the groundwater condition, which is saturation significantly lowers the strength of most soils compared with their values when dry. So certain soils weaken to a stage at which they run like a viscous liquids. High pore pressure of a groundwater in a layer or any plane of weakness lowers frictional resistance to movement. So this mechanism is the same as the which follows a hovercraft to glide over water or land on high pressure cushions of air. So we have and tragedy, a disaster in Aberfan on 1966, when a spoil heap of mine waste slid downwards onto a Welsh village, enveloping and destroying a large part of the local school. We have also stresses produced by natural loads adjacent to the cutting. Step-sided valleys or mounds affect the state of stress in the ground near the surface, not only below themselves but also for some distance around. This lateral change in stress conditions may be sufficient to cause instability of weak rocks and soils. Also, we have other geological factors causing instability of existing slopes. An initially stable slope may become unstable with the passage of time because of human disturbance. This may consist of adding a fresh load such as spoil heap, removing support by excavating, or triggering movement by vibration from nearby heavy machinery. So, we have a common geological causes that cause an instability of existing slope. First, we have the withering. Withering of the soil or rock of the slope so that it becomes weaker. This may affect the bulk of material, for example, the boulder clay, or may be concentrated along planes in a rock. Chemical alteration of existing minerals is important under certain conditions, as is mechanical breakdown in others. We have periglacial withering in Pleistocene times also affects the stability of some present-day cliffs. Erosion of the slope by a river or natural agent, usually at its base but possibly along a weaker layer or plane, may cause undermining to take place. Also, the change in water content of the soil or rock. Heavy rain, especially after the drought, saturates the material forming the slope, increasing its mass and gravitational pull on a given volume, and also reducing the strength of soils and fractions along any discontinuities. There are types of failure of soil slopes. Instability of soils on a slope may take one of the following forms. One of these is creep. Creep occurs on a steep slopes and produces a downhill movement at low rates, less than 10 mm per year, of the top few meters of soil. It is facilitated by the effects of frost and by heavy rain washing out fines from soil. Any excavation on a slope affected by creep is likely to increase movement. Creep may be recognizable by displacement of fencing or for cover of turf, or by the drag effects of strata under the soil. We have also flow. It is a rapid movement of waterlogged soil, broken rock, and mud downhill. It is usually happen after a prolonged rain occurred. Scree or talus slide occurs where rock fragments fall off a fractured rock mass which has been subjected to mechanical weathering. They rest at a natural angle of repose at the foot of the slope. Excavation at the foot of the scree slope or inadequate drainage, which increase pore water pressure in mass, will lead to instability of the slope. The third is the translational failure, involves in movement along a particular plane of weakness in the soils of the slope. For example, in a slope form of a clay layer in the sand layers, deterioration of the shear strength of the clay may lead to movement at the boundary of the clay and sand. Failure of this type may occur with the slope angle as low as 6 degrees. Lastly, we have rotational slip. Rotational slip affects clay or clay-rich rocks such as mudstone and shales. The surface of movement is curved, and is such that shear resistance along it is assumed to be given by the equation of the shear resistance is equals to the cohesion added to the difference between the stress normal and the pore water pressure times the angle of the frictional resistance of the clay. Rotational slip is usually preceded by the development of vertical tension cracks at the top of the slope. This slide shows the legends of the shear resistance equations. So we have the stress normal to the surface, pore water pressure, cohesions of the clay, angle of fractional resistance of the clay, and the shearing resistance. There are also types of failure of natural rock slopes. So one of these is the minor rock falls. Minor rock falls are produced by weathering acting on unstable rock slopes. The susceptibility of given rock to weathering processes can be estimated by determining its saturation moisture content and the swelling coefficient. Igneous and high-grade metamorphic rocks with its values of less than 1% are generally safe from weathering effects. In this slide, we see two pictures. On the left side, we see an example of a minor rock falls. On the right side, we can see an example of an igneous rock. Sedimentary rocks and low-grade metamorphic rocks are considered to be safe on slopes if their values are less than 3%. If exposed rocks on a slope have high saturation moisture contents, and then tests should be carried out over a period of time, under both freeze-thaw and wet-dry conditions, and their swelling behavior are noted. Ice action is important if joints are present. If the rock mass has a low black volume that is less than 0.5 cubic meter, minor rock falls may occur, even if the rock has a low saturation moisture content. There are also major rock falls, which is usually result from collapse caused by undermining of rocks above a weak layer. The agent may be weathering, erosion, or mining. Common weaknesses in a rock mass which can lead to collapse after weathering and etching out by erosion are layers of clay rock, chlorite in joints, and carbonate rocks, including calcareous sandstones. Translational failure along a particular plane of weakness may occur in the rock mass cut by faults, master joints, or step bedding planes. The shear strength of the infill in these discontinuities determine the stability of any slope cut in the rock mass. As in soils, the shearing resistance along any plane is given by the equation of the shearing resistance equals to the cohesion between two sides of discontinuity added to the difference between the stress acting normal to the plane of discontinuity and the water pressure in the discontinuity, times to the angle of the frictional resistance attributed to the plane of movement. Friction angles for materials commonly found in filling joints are given, as also are some representative values of unconfined compression strength of rocks. If the discontinuities are infilled with weak material, such as clay, stability of a slope in such rock mass will depend on its shear strength. Where a rock mass consists of alternating layers of strong and weak rocks, tests in situ in the laboratory are necessary to determine whether failure is likely to occur because of the shear failure in the weak bands, or because of sliding along the bedding planes if they dip steeply.
Rotational failure. It occurs when the stress generated by gravity on rocks near the slope exceed the inherent strength of the rock mass. That may be accompanied by translational failure. The extra load of a spoil heap may trigger this failure. Ngayon, there are three different ways kung paano nangyayari yung rotational failure. First is face failure or slope failure. Second, toe failure. And last, the base failure. Ang madalas mangyari dito is yung toe failure. And madalas na nangyayari ang rotational failure sa mga lugar kung saan merong infinite slopes such as earthen dams, embankments, and man-made slopes. Ang rotational failure ay nangyayari kapag kayong surface ay nagsimulang gumalaw outwards and downwards. Face failure or slope failure. It occurs when soil above the toe contains weak stratum. In this case, the failure plane intersects the slope above toe. Toe failure. It is the most common failure in which failure plane passes through the toe of a slope. Base failure. It occurs when there is a weak soil strata under the toe and failure plane passes through the base of slopes. Makikita natin yung mga failures na to kung paano ba siya nangyayari dito sa picture sa taas. Creep failure. It takes place when certain rocks such as clays absorb water, swell, slowly deform and move downhill. If they are overlain by a more stable, stronger layer, translational failure may take place along the bedding plane between them. Creep failure is time-dependent and permanent deformation of a material when subjected to a constant load or stress. This deformation typically occurs at elevated temperatures, although it may occur under ambient temperature as well. So, nangyayari ang creep failure kapag yung material natin is lumambot, na-deform, and gumalaw downhill. And kapag yung material natin is always subjected under a constant load or stress. Aside from this, yung temperature natin has also may ambag siya dun sa creep failure kung bakit ba siya nangyayari. 4 common measures taken to prevent slope failures. First, the slope is modified by removing material from the potentially active part of the slope and adding it to the toe of the slope. Second, the slope is drained to reduce load and increase strength of frictional forces by means of trenches filled with rubble. Third, the slope is supported by a retaining wall or by embedded piles which are anchored to the rock mass. The soil and rock behind the wall must be drained. Fourth and last, an unstable rock face may be stabilized either by bolting or by using steel mesh. Bolting is used to anchor large unstable blocks and the steel mesh to cover entire sections of an unstable steep rock face. Where such unstable slopes exist, for example, in a new road cutting, sufficient shoulder width should be allowed to absorb debris and a side ditch excavated with to or without a rock fence to prevent the new road. Maaaring nakakita na rin tayo ng isa sa mga ganito and madalas siyang makita dun sa mga areas kung saan prone yung landslide. Kung sa mga nakikita natin, kung maaalala natin, merong mga nets or steel mesh doon para ma-avoid yung pagguho ng lupa. And sa iba naman, yung mga recraft, makikita natin may mga bato and may matibay na concrete para hindi mag-landslide. And beside doon, meron din silang nilalagay na mga pipes in order to drain para hindi bumigat and lumambot masyado yung lupa natin para mapanatiling tuyo and yung tubig natin is doon dadaan. Yung picture na to is nagpapakita ng one of the largest excavation ng solid rocks sa UK noong 1970s. The gritstone group bands are unaltered but the thin shelly layers contain some chloride produced by very slight thermal metamorphism. The strata dip angles ranging between 13 degrees and 21 degrees to the southwest. The bedding plane discontinuities present little problem of instability and a vertical cut, but it is also a second important set of discontinuities that strike roughly parallel to the highest face of the excavation and dip steeply towards it. Discontinuity. Discontinuities are small reverse fault and has broken rock adjacent to them to make the rock mass inhomogeneous, potentially unstable in vertical cuts and awkward to excavate. For example, a flat floor is an essential feature, but because of discontinuities, it was difficult to achieve as mechanical shovels tended to gouge the fracture zones preferentially and to over-excavate locally. It also proved difficult to blast clean-angled benches on the excavated face and raised the important question of what angle of slope we needed to make them safe. So, discontinuities are yung mga faults na kung saan nagpapahirap sa excavation process na ginagawa natin. This is a sample of discontinuity data table.
An important consideration for selecting a suitable site for a reservoir is that the rocks and soils around it should naturally form an impermeable basin. Other factors to consider are the consequence of a change in the position of the water table as the reservoir fills, and the rate at which sediment will accumulate. Wells. The important sources of leakage from the reservoir are A. Through the permeable soils, B. Through rock aquifers, and C. Along faults and master joints. The first one is A. In regions that have escaped glacial erosion, there may be a thick mantle of weathered rock forming a permeable soil. Other deposits, particularly sand and gravel, may offer paths for leakage. A change in the water table as the reservoir fills may affect the stability of hillside and it can cause landslide. The second one is B. Leakage through rock aquifer is controlled by their structure and their relationship to hydraulic gradients. Leakage along the sandstorm layer are shown in the figure 7.7 would take place in structure A but not structure B, as shown in the figure below. In general, dips of the aquifer towards a reservoir inhibits leakage along it. Spring and seepage may be useful in indicating the position of the water table. Ideally, a reservoir should be sited on impervious rock or in syncline plunging upstream. The last one is C. If the reservoir is sited on limestone, extra effort and resource must be spent to locate and seal all the faults and joints. In glaciated valleys, incipient plucking of the rock surface by ice has opened fractures to produce slip joints. This may be present at depth up to 20 meters. Large dams are almost invariably founded on strong solid rock, and the thickness of any cover of soils and the strength of rocks at the dam site are important factors in geology. Mapping the position of rocks head over a glacial rock basin may add significantly to the cost of exploring a dam site. Seismic refraction surveys should be used combined with borings to define rock heads. Particular attention should be paid to mapping fractures which might behave as zones of seepage from the reservoir. Case history: leakage from Crubyandian Dam, Midlothian, Scotland. The Crubyan Dam is a small earth dam built in 1850, which impounds water for seasonal storage. Leakage had persisted over a long period, which eventually some local collapse and free flow into the ground. The succession of strata at the dam site will shown in Figure 8. The impermeable cover of boundary clay, which might have afforded some protection against leakage, has been replaced by a much more permeable surface. Leakage and subsidence were due to seepage through the sandstone, which had increased as solution cavities formed. In Figure 8.8, geological map of the area around Clubian Reservoir. When the reservoir was refilled, leakage was only 1% of the previous amount, according to tests carried out by Chinese state-run Xi'an news agency.
Geology of tunnels. Geological consideration in tunneling. The area in which a tunnel is built is determined by its purpose, but the decision to tunnel, rather than, say, build a bridge, is influenced by the relative geological difficulties, and the precise line of tunnel may be determined by a choice of favorable or difficult local geological conditions. The geological factors considered in tunneling projects are as follows. The first, we have the ease of extraction of the rocks and soils. The second one is the strength of the rocks and the need to support them. Next, we have the amount inadvertently excavated beyond the perimeter of the tunnel outline. That is, overbreak, particularly where explosives are used. Next is the groundwater conditions and the need for drainage. And lastly is the temperature in very deep tunnels and the need for ventilation. Methods of excavation. The main problem in constructing tunnel through non-cohesive soils or weak rocks is to support the ground rather than to excavate it. Excavation is usually done by a soft ground tunneling machine fitted with a rotary cutting head. This may have a full-face rotary breasting system which remains in contact with the soil face as the cutter head moves. The principal factor controlling rate of progress and cost in constructing a tunnel in strong rocks is usually relative ease of excavation. The traditional method is to blast out successive sections of the tunnel by drilling a pattern of holes in the rock, charging them with explosive and firing. The need for any support and the type of support used are dependent on the relative stability of the roof and walls of the tunnel. Complications arising from local geological conditions. In soft rock tunnels, heterogeneous rock or variable conditions at the face can produce serious problems and add to costs. A boulder clay or the soil containing large pebbles creates a near impossible problem for existing slurry face machines. Hard rock rolling cutters can cope with hard boulders but have difficulty in other soft soils. A mixed phase of hard rock and wet non-cohesive soil presents an even worse headache to the engineer. The variation in strength of the soils along the tunnel line should ideally be anticipated so that appropriate support can be used while the face is being excavated. Inability to do so can result in over-excavation. Excessive overbreak and the risk of rock falls from the roof are most likely in the following conditions. fault zones, especially if they contain loosely cemented branches. At dikes, narrower than the tunnel, which have well-developed horizontal cooling joints. At cyclical axes, as the tensional joints develop at the hinge of the fold diverge towards the tunnel and the blocks are not supported. At layers of loosely compacted fragmental rocks, such as some volcanic benches, and where the layers of strong and weak rocks, for example, alterations of limestone and shales, are present at the level of the roof and strike along the tunnel and have steep dip. The ideal tunnel outline is shown by the heavy broken line. The strata to be excavated are alternating shales and well-jointed limestones, dipping steeply and striking parallel to the tunnel. The actual amount pulled out by explosives along the planes of weakness is indicated by the heavy black line. This excess rock excavated beyond the perfect section is called overbreak. The amount of seepage into a tunnel through previous rocks and joints may be a significant factor in design. It must be assessed from a knowledge of groundwater conditions, bulk permeabilities of rock, and the geological structure. For example, crystalline rocks, such as granite, gneisses, and schists, are typically dry except for flow along joints and faults, and perhaps at the margins of any dikes which cut them. In previous rocks, the flow of groundwater into the tunnel is likely to increase at fault zones and at cyclical axes, which tend to channel flow towards the tunnel.